Good morning, I am Aditi studying in BSc Chemistry Honours second year. Today in this video we are reading acids and bases of inorganic chemistry. Arrhenius concepts of acid and bases. Arrhenius, a Swedish chemist, was the first to define acids and bases in aqueous solutions. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which when dissolved in water gives hydrogen ions H positive. Accordingly, all mineral acids like HCl, HNO3 and H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ions. As look at this. Arrhenius named these acids which dissociate completely in water as strong acids. There are other acids like acetic acid, carbonic acid and phosphorus acid which when dissolved in water do not dissociate completely into ions. As a result, an equilibrium is set up between the ions and the undissociated acid molecule as shown below. Arrhenius named these acids as weak acids. According to Arrhenius, a base is a weak substance which contains hydroxyl group and which when dissolved in water gives hydroxyl ions. Thus substances like NaOH and KOH which when dissolved in water dissociate completely to give hydroxyl ions. Arrhenius named these bases which dissociate completely in water as strong bases. These are the substances which do not completely dissociate into hydroxide ions. Arrhenius named these substances as weak bases. For example, substances like NH4OH, MgOH2, AlOH3 do not dissociate complete to give OH negative ions and can be written as hydrogen ions obtained from the acids and hydroxyl ions obtained from the bases combined together to form unionized water. Arrhenius described this combination of H positive and OH negative ions as neutralization reaction. Combining right hand sides, cancelling the common ions on both the sides. Arrhenius concept is a very simple to apply and explains a number of phenomena like neutralization, hydrolysis of salts in strength of acids and bases. However, there are certain limitations which are described below. Arrhenius' concept of acids and bases is applicable only in aqueous solution. This concept fails to explain the acid or base behavior of substances in non-aqueous medium such as liquid ammonia, liquid sulfur dioxide, alcohol, etc. Arrhenius' concept fails to explain the acidic character of substances like CO2, SO2 and SO3, etc. and basic character of substances like NH3, Na2CO3, CaO, etc. Arrhenius' concept also fails to explain the reaction between an acid and a base in the absence of water, for example. Although Arrhenius' concept of acid and base suffers from a number of limitations, yet the concept is very useful and informative for an elementary approach. Bronsted-Lowry concept. Arrhenius' concept of acids and bases was further improved by Bronsted and Lowry. Both Bronsted, a Danish chemist, and Lowry, an English chemist, in 1923 incidentally introduced the same definition for acids and bases. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton, whereas a base is a substance which can accept a proton. In other words, an acid is a proton donor, whereas a base is a proton acceptor. As a result, Lowry-Bronsted concept is sometimes called the proton donor acceptor concept. It can be represented as, according to Bronsted-Lowry, a neutralization reaction involves the release of the proton by an acid and the acceptance of the proton by a base. For example, the reaction between HCl and NH3 to form the salt ammonium chloride can be represented as. Curved arrow shows how electrons must rearrange to result in the transfer of hydrogen atom from the acid to a base. The unshared pair of electrons on the nitrogen of ammonia is attracted by the partial positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of the structure of the reactants and products shows that the hydrogen atom, which was bonded to chlorine in the reactants, is bonded to nitrogen in the product. Thus, a proton has been transferred from chlorine to nitrogen. To act as a Bronsted-Lowry base, a species must have at least one unshared pair of valence electrons so that it can form a covalent bond to the proton. To act as a Bronsted-Lowry acid, a species must contain at least one hydrogen atom that is attached to an atom that is more electronegative than hydrogen. In this case, HCl loses a proton and is an acid. Ammonia accepts a proton from HCl and is a base. Some other examples of acid-base reactions according to Lowry-Bronsted concept are: it is important to note in the above examples that water acts as a base with respect to hydrochloric acid and sulfuric acid. Interestingly, water acts as an acid with respect to ammonia. Such a substance which acts both as an acid proton donor as well as base proton acceptor is called amphoteric or amphiphotic substance. Similarly, bicarbonate ion behave as an acid and a base. Other example of amphoteric substance is hydrogen sulfate ion. Conjugate acid-base pairs. Let us reinvestigate a reaction between an acid and a base. HCl being an acid donates a proton and from Cl ion, whereas ammonia being a base accepts a proton and form ammonia ion. Now the chloride ion has a tendency to accept the proton, whereas ammonium ion has a tendency to donate a proton. In other words, an acid donates a proton and becomes a base, and a base accepts a proton and becomes an acid. Thus, a base formed from an acid is regarded as the conjugate base of the acid. Similarly, formed from a base is called the conjugate acid of the base. In the example above, between HCl and NH3, Cl negative ion is the conjugate base of HCl and NH4 positive ion is conjugate acid of the base NH3. Acids and bases that are related by the laws of chain of H positive ion are called conjugate acid base pairs. Thus, Cl negative and HCl, NH4 positive and NH3 are conjugate acid base pairs. We can represent the acid base. It clearly indicates that an acid-base reaction would involve two acids and two bases. These acids and bases are called conjugate pairs. For example, in the above example, HCl is an acid since it donates a proton and Cl negative is its conjugate base. Water accepts the proton and hence is a base. Thus, H3O positive ion is the conjugate acid. A strong acid has a weak conjugate base and vice versa. Some other examples of conjugate acid base are cited below. Look at this. It is further important to note that the Bronsted-Lowry concept is not restricted to only neutral molecules. The concept is equally applicable to ions as well. A careful inspection of the above discussion reveals that. Substance is capable of showing acidic character only if the other substance is capable of accepting the proton base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene does not accept H positive ion from HCl. Not only neutral molecules but cations and anions may act as acid or bases. Both Arrhenius and Bronsted-Lowry concept require an acid to be a source of proton. Thus, all Arrhenius acids are Bronsted-Lowry acids. According to Arrhenius, a base is a substance which gives OH negative ions in solution. Whereas according to Bronsted-Lowry, a base is a substance which can accept a proton. For example, carbonate ion, bicarbonate ion. Carbonate ion can give OH negative ions in aqueous solution. It therefore cannot be an Arrhenius base. The sole Bronsted-Lowry bases are not Arrhenius bases. Limitations of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcoming of Arrhenius concept, yet it could not answer some of the well-established reactions. For example, it cannot explain the reaction between acidic oxides like CO2, SO2 and SO3 with the basic oxides like CaO, BaO and MgO which take place even in the absence of water, for example. Clearly, in the reaction between CaO and SO3, there is no proton transfer involved in the reaction. The acidic nature of compounds like BF3, FeCl3 and AlCl3. Lewis concepts of acids and bases. G. N. Lewis in 1923 proposed a more general definition of acids and bases which is based upon the donation and acceptance of electron pair. According to Lewis' concept, an acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbitals to accommodate one or more pair of electrons can act as a Lewis acid. On the other hand, a base is an electron pair donor. It means that any substance with unshared pair of electron can behave as a Lewis base. Thus, the acid-base or neutralization reaction involves the formation of a coordinate bond between the electron pair donor and the electron pair acceptor. For example, the reaction between boron trifluoride and ammonia is a typical Lewis acid-base reaction. Let us now discuss in detail. Lewis acids. According to this concept, Lewis acids are classified as molecular having central atom with incomplete octet of electrons. Boron trifluoride, aluminum trichloride, etc. are acids of this type. It is clear that central boron and aluminum atom have only 6 electrons. Simple cations. All the cations are short of electrons and can behave as Lewis acids. Large-sized cations like Na positive, K positive, Ca2 positive and Ba2 positive, etc. behave as weak Lewis acid. This is because these have little tendency to accept electrons. On the other hand, small-sized cations such as H positive, Ag, Li ions have a strong tendency to accept the pair of electrons and are strong Lewis acids. In addition, highly charged cations have a higher tendency to accept electron pairs relative to lower charge cation of the given metal. For example, as a strong Lewis acid. Some of the typical examples of Lewis acid base reactions are given below. Look at this. Molecules in which the central atom has available d orbitals and may acquire more than 8 electrons. Compounds such as AlCl3, SiF4, SnCl4, SbF5 and SO3 are Lewis acids where the central metal atom can be expand its valence shell. Molecules with a multiple bond between atoms of dissimilar electronegativities. Carbon dioxide represent an interesting example of a double bond between carbon and the more electronegative oxygen atom. Oxygen, being more electronegative, has a tendency to attract the shared pair of electron more towards it and CO2. As a result, it acquires positive charge on the carbon atom and becomes electron deficient and attaches with the oxygen of the hydroxide ion Lewis base. Similarly, sulfur trioxide acts as a Lewis acid towards water. Lewis bases. According to this concept, Lewis bases may be classified as one of the following types of substances. Negatively charged anionic species. All the negatively charged species are Lewis base because they are rich of electrons and have a strong tendency to donate electron pairs. Common examples are: the greater the charge density on the anion, the stronger is the base. Neutral molecules with one or more than one shared pair of electrons. Molecules with unshared pair of electrons act as a Lewis base. For example, NH3, H2, R2 and R2C double bond O act as a electron donors. Alkenes and alkynes with multiple bonds also form coordinate bonds with metal ions in organometallic compounds. Acid-base reactions according to Lewis concept. Some of the typical acid-base reactions involving the formation of a coordinate bond between a Lewis acid and a Lewis base are summarized below. Combination between H positive and NH3. Combination between BF3 and F negative ion. Combination of calcium oxide and sulfur trioxide. It is important to note that an empty orbital is being created on the sulfur atom by moving a pair of electrons from the double bond on the oxygen atom. Combination of cupric ion with ammonia. Combination of stannic chloride with ethers to give an adduct. Lewis acid base concept discussed above is widely used because of its simplicity. Many acid base reactions, in spite of its wider applications than Arrhenius and Bronsted-Lowry concept, has several disadvantages which are discussed below. Lewis concept is too general and consider all reactions forming a coordinate bond base reaction. This is, however, not true always. According to Lewis concept, transition metals that form compounds with carbon monoxide are acid base reaction, which is not correct. Formation of a coordinate bond between an acid and a base is the base of Lewis concept. The well-known acids like HCl, HNO3 and H2SO4 do not form any coordinate bond bases such as NaOH or KOH. Accordingly, HCl, HNO3 and H2SO4 should not be acid according to Lewis concept. Lewis concept does not give any uniform scale of acid and base strength. Lux flood concept of acid and base. A new concept of acid and base was proposed by Lux in 1939. This concept was further 1947. According to Lux flood concept, an acid is any substance which accepts, whereas a base is any substance which gives an oxide ion. Lux flood bases can be represented as Lux flood acids can be tentatively represented as. Thus, Lux flood acid base reactions can be represented as according to Lux flood concept, substances that show a tendency to lose as well as gain an oxide ion are termed as amphoteric. Zinc oxide represents an interesting example of amphoteric character. For example, zinc oxide can lose O2 negative ion to form Zn2 positive ion in addition to zinc oxide gaining as O2 negative to form ZnO2 to zincate ion. Similarly, Al2O3 can behave both as an acid as well as a base in Lux fluid sense and hence act as an amphoteric. This concept of Lux fluid is very useful at high temperature, especially in glass ceramic industry and metallurgical operations. The concept of Lux fluid can also be extended to halides and sulfides in place of oxygen. For example, the sandwich concept of an acid and a base. The sandwich concept of acid and base is very general and takes into consideration all the concepts of acids and bases proposed by Arrhenius, Lowry, Bronsted and Lewis acids. In addition, the sandwich concept includes all oxidizing agents as acids and all reducing agents as bases. Thus, according to sandwich concept, as an acid is a substance that reacts with a base, gives off cations, accept anions or electrons. Similarly, sandwich concept defines as a base as substance that reacts with an acid, gives up anions or electrons to combines with the cation. Some of the examples of acid-base reactions in the sandwich sense are illustrated below. Look at these examples. sandwich concept is very useful as it classifies all examples of acid and bases is too general. This is because it considers even the oxidation reduction redox reactions. Solvent system concept. The solvent system concept of acids and bases was postulated by Cady Estelle in 1928 to the Lowry-Bronsted concept and is applicable to both protonic as well as non-protonic solvents to this concept. An acid is a substance which either by direct dissociation or by the interaction with the cationic characteristic of the solvent. A base is a substance which either by direct dissociation or by the interaction with the anionic characteristic of the solvent. The characteristic cations and anions of the solvent are the anions produced during the prefix auto means itself. To illustrate this concept, let us consider the autoionization and non-protonic solvents. Look at this. For example, HCl behaves as an acid in water solvent as it gives the cationic character water. Similarly, NH3 acts as a base in water as it gives the anionic characteristic. It is important to note that the acetic acid behaves as an acid in water as it produces characteristic of water. Acetic acid behaves as a base in sulfuric acid as it produces the anionic characteristic solvent sulfuric acid. Urea dissolves very readily in water and gives neutral solution. However, urea dissolves ammonia and behaves as an acid base. It gives the cationic characteristic. Similar to Arrhenius concept, neutralization reaction may be represented as the combination of cationic characteristic of the solvent with the anionic characteristic of the solvent to form the solvent molecule in non-aqueous medium. Some of the neutralization reactions in various solvents are given below. It is important to note that the neutralization according to solvent system concept is the reverse of autoionization reactions. Types of solvents. Solvents are classified in a number of ways on the basis of their physical and chemical properties broadly. There are three ways in which solvents can be classified. Protonic and aprotic solvents. Solvents which contain hydrogen and can lose hydrogen in the form of proton are called protonic solvents. Common examples of protonic solvents are H2, NH3, H2S, HF, etc. Solvents from which hydrogen cannot be obtained in the form of proton are called aprotic solvents. Common examples are CH3, CnC6, H6, etc. Solvents like N2O4, SO2 and CCl4 are also called aprotic solvents. Acidic, basic and amphoteric solvents. Solvents which have a strong tendency to give protons are called acidic solvents. Common acidic solvents are H2SO4, HF, CH3, COOH, etc. Solvents which have a strong affinity for protons are called basic solvents. Basic solvents are ammonia, NH3, hydrazine, pyridine, etc. Solvents which display both acidic and basic properties are called amphiprotic solvents. Example of amphiprotic solvents are water, methyl alcohol, etc. Ionizing and non-ionizing solvents. Solvents which undergo self or auto-ionization are called ionizing solvents. Typical examples of ionizing solvents are water, ammonia, hydrogen fluoride, sulfur dioxide, etc. Solvents which do not ionize are called non-ionizing solvents. Typical example of non-ionizing solvents are benzene, carbon tetrachloride. Such solvents are non-polar and have low dielectric constant. Relative strength of acids. The strength of protonoic acids can be compared easily by the tendency of the acids to give protonic acid like HCl, H2SO4, HNO3 ionize completely to give protons, whereas acids like CH3COOH and HCl ionize completely to give protons. The acids which ionize either completely or to a very extent are named strong acids. On the another hand, acids which ionize to a smaller extent are named acids. Thus, protonic acids, namely HCl, H2SO4, and HNO3, are strong acids, whereas CH3COOH, HF, HCN are weak acids. Let us consider the ionization of an acid Ha, which is represented as the equilibrium constant Ka for the reaction is written as, where A are the concentration and the undissociated acid, known as the dissociation constant or ionization constant of the acid. The magnitude of Ka measures relative strength of the acid. The stronger the acid, the larger is the value of Ka dash. It is convenient to use the term pKa analogues to pH to express the dissociation of an acid. A larger value of pKa means that the acid is little dissociated. It implies that the acid is weak. Larger the value of pKa, the weaker is the acid. Dissociation constants of some of the common acids are given in table 7.1. Table 7.1, dissociation constants of some acids in water. Look at this table. A close inspection of table 7.1 reveals that the strong acids have negative pKa value of acids are given in the table. HBr is the strongest acid. Trends in acid strength. We have learned that the relative strength of acids in aqueous solution can be easily expressed in of pKa value. The higher the value of pKa dash, the weaker is the acid, and vice versa. The pKa value binary anhydrides are given in table 7.2. However, substitution of electron withdrawing groups in the benzene ring increases the acidity of benzoic acid by resonance effect. The resonance effect of nitro group is more dominant in the ortho and para position, but it not in the meta position. Some of the pKa values of aromatic acids are given below. Look at this. Of the four benzoic acids given above, orthonitrobenzoic acid is the strongest acid. If it is because the ortho group is nearest possible from the carboxylic acid groups and exert both the inductive and resonance effect effectively. Effects of solvent on the acid strength, leveling effect. The strength of an acid or a base depends largely on the nature of solvent used for its dissolution. Let us consider the dissolution of hydrogen chlorous acid in three different solvents, viz. Ammonia, water and sulfuric acid. One can clearly see that HOClO is a strong Bronsted acid in NH3, a weak base in strong, and a strong base in H2SO4. The acidity and basicity of a protonoic solvent plays an important role in choosing a solvent for a chemical reaction. The strongest acid which is available in a protonoic solvent is that which results from the self-ionization of the solvent. Likewise, the strongest base available is that which results from the self-ionization of the solvent. Let us consider, for example, the following auto-ionization reactions. In aqueous solution, the strongest acid which can exist and which can be available for the reaction is hydronium ion. It means all the strong acids known to the chemist appear to have exactly equal strength in aqueous solution. This results from the fact that acids such as perchloric, hydroiodic, hydrobromic, and hydrochloric acids all are stronger proton donors than is the hydronium ion. Thus, all these acids react completely with water to give hydronium ion. It means that acids stronger than H3O positive are leveled to the strength of H3O positive when placed in aqueous solution. In other words, water levels all the strong acids, namely HClO4, HI, HBr, HNO3 and HCl to the strength of H3O positive as shown in the figure 7.2. Look at in the figure 7.2. Similarly, the very strong bases such as hydroid ion, anide ion and ethoxide ion all react completely in aqueous solution to yield hydroxide ion. It means that all these strong bases are labeled to the strength of OH negative ion on reaction with water. In other words, solvent water levels all strong bases to the strength of OH negative ions. For example, when sodium hydride NaH is added to water, a vigorous reaction occurs with the basic evolution of hydrogen gas and the resulting solution is found to be a solution of hydroxide. Similar reactions occur when other bases like NaNH2 and sodium ethoxide are added to water. In order to compare the relative strength of strong acids and bases, the selection of the solvent is very important. The solvent selected should be such that it ionizes the strong acids and bases to different extents, such a solvent which ionizes the acids and bases to different extents is called a differentiating solvent. Acetic acid can be used as a differentiating solvent because strong acids like HClO4, HI, HBr, HNO3 and HCl will ionize to different extents in acetic acid. Acetic acid is a poor proton acceptor. Perchloric acid reacts completely, protonates completely acetic acid as. Whereas other acids do not react completely because of incomplete protonation of acetic acid by these acids. On the basis of the relative strength of different ionization of these acids in acetic acids can be arranged in the order. Look at the order. Acetic acid is a leveling solvent toward bases such as CnOH, OC2H5 and NH2. This is because acetic acid reacts with the bases and level them to the strength of acetate ion. However, strongly bases solvents such as liquid ammonia act as a differentiating solvent towards bases. Thus, it may be concluded that acidic solvents tend to differentiate between acids and level of bases, whereas basic solvents tend to differentiate between bases and level of acids. To summarize, all acids and bases stronger than the characteristic auto-ionized ions of the solvent will be leveled off by the solvent, whereas acids or bases weaker than the auto-ionized ions of the solvent will remain in equilibrium. Strength of oxoacids. The hydroxides of reactive metals are ionic compounds and are strong bases. However, hydroxides of non-metals are molecular compounds and are acidic. The oxo acids can also be considered as the derivatives of water and can be represented by the formula EOH, where E is the non-metal which determines the acidity of the compound. The strength of the oxo acid depends upon the combined effect resulting from size of the atom E, electronegativity of the atom E, and Inductive effect of the substituents present on E. A small and highly electronegative atom E will pull the shared pair of electrons between E-O bond more towards itself. In turn, the oxygen will pull electrons from hydrogen atom in the OH bond and makes the proton to dissociate easily. This makes the compound EOH to behave as an acid. Thus, higher the electronegativity of E, the more easily the proton is lost, and consequently stronger is the acid oxoacid. The acidic character of the oxoacid halogens decreases in the given order, as is evident from the pKa values. The acidities of the oxoacids are also related to the number of additional oxygen atoms, oxygens that are not part of OH groups, attached to the atom E. In these compounds, the acidity increases with increasing oxidation number of the atom E. In the series of oxoacids of chlorine, the acidic strength increases in the following order. All these acids have only one protonated oxygen, that is only one OH group. Perchloric acid has 3, chloric acid has 2, and chlorous acid has 1 atom additional oxygen atom. These additional oxygen atoms tend to withdraw more electron density from the hydrogen through the intervening chlorine atom. As a result, the polarity of the OH bond increases more in case of acids containing larger number of oxygen atoms. As a result, the tendency for the proton to dissociate increase in the order. Look at the increasing order. In general, oxoacids without extra oxygens are weak. Oxoacids with one extra oxygen atom are moderately strong, and oxoacids with 2 or more extra oxygens are strong acids. Alternatively, the increase in the acidic strength of can be explained in terms of the stability of the conjugate base formed by the loss of H positive ion from the corresponding acid. Let us consider all the non-hydroxylic oxygen atoms attached to the chlorine atom by a double bond. Ionization of a proton from the OH bond forms an anion that is stabilized by the charge distribution the entire ion. The greater the number of pi or double bonded O atoms, the greater is the delocalization, the charge, and consequently the stronger is the acid. The charge distribution is minimum and maximum in ClO4 ion. It means that ClO ion will have minimum stability and hence maximum attraction. This makes HOCl the weakest acid. On the other hand, ClO4 ion will have maximum stability and minimum attraction of H positive ion. This makes HClO4 the strongest acid. Look at the increasing stability. We have already learned that with the increase in the oxidation state of the central atom, the acidity of the acid increases. Thus, the order of the increase in the acidic strength of oxoacids of chlorine is the same argument of increased acidity with increase in the oxidation state can be extended to and in case of sulfur acids. However, this generalization does not apply in case of oxoacids of phosphorus. The important oxoacid of phosphorus are H3PO2, H3PO3 and H3PO4, in which the oxidation number of phosphorus +1, +2 and +3 is respectively. The expected order of their increasing strength is, look at this. However, experimentally, all the oxoacids of phosphorus have been found to weak acids with increasing acidic strength in the order. The discrepancy in their acidic strength can be explained if we take into consideration the molecular structure of these acids, as shown below, which contains the pH and P double bonds rather than the POH linkages only. When to a solution of a strong base such as potassium hydroxide is added, protons are transferred from the hydrated ion to the base. The following reaction take place are: addition of OH ion shifts all the four equilibria shown above to the right as hydroxide ions are added to a solution containing ion insoluble. Return frequently as AI is precipitated out, which dissolves in the presence of excess of OH ion. If a solution of a strong acid is added to a solution containing AlOH4 negative ions, H positive reacts with OH ion to form water. As OH is removed, all four equilibria shift to the left, insoluble precipitates and redissolves. Similarly, the hydroxides of chromium. It is important to note that when protons are transferred from hydrated cations, as OH bond breaks just as it does when protons are transferred from oxoacids. Equilibria constants for the hydrolysis of hydrated cations be measured. Equilibria constant of some common metal cations are given in table 7.5. Look at the table 7.5. Value of Ka and pKa of some hydrated cations. Thus, the order of acidity among alkali metals ions is. It is obvious that the acidity of hydrated cations of alkali and alkaline earth metals decreases. Group of the periodic table. If radii and electronegativity are similar, as in the case of Na positive and Ca2 positive, then the higher the charge on the cation, the more acidic the hydrated ion. If one moves across a row of the periodic table from left to right, ionic radius decreases and charge increases. As a result, acidity of the hydrated cation increases across a 4-row example. If a charge and radius are similar, the greater the electronegativity of the metal, the more acidic the hydrated cation. Let us compare the case of Mg2 positive and Zn2 positive. In case of zinc, the electronegativity is more, hence the cationic zinc is more acidic than magnesium. The hydrated Al3 positive ion with the high charge, small radius and relatively high electronegativity is by far the most acidic cation listed in the table 7.5 above. Role of solvent on their strength of Lewis acids and bases. A solvent plays an important role on the strength of Lewis acid and base. A Lewis acid on hydrolysis may produce an acid stronger than the Lewis acid itself. For example, boron trifluoride, which is a Lewis acid, undergoes hydrolysis with the evolution of hydrogen chloride. The sequence of steps involved in the hydrolysis are outlined below. The first step involves the attack of water molecule with its lone pair of electrons on the vacant 2p orbital of boron. A lone pair of electrons from water is donated to the empty orbital of boron with the formation of a coordinate bond. The second step involves the loss of one HCl molecule. In doing so, one of this chlorine of BCl3 is replaced by one OH group. The third step involves the repulsion repetition of the above steps till all the chlorines are replaced by the hydroxyl groups and one gets boric acid. Another interesting example where the role of solvent is greatly appreciated is the hydrolysis of silicon tetrachloride to afford silicic acid, the distinguished feature in the hydrolysis of boron trichloride and silicon tetrachloride in the presence of vacant d orbital in case of silicon. The mechanism of hydrolysis is the same, expecting that the water molecule attacks the vacant d orbital of silicon, forming an adduct involving a coordinate bond between silicon and oxygen. The adduct form loses HCl molecules in steps till all the chlorine atoms are replaced by OH groups, yielding finally silicic acid SiOH4 are shown below.